And now we'll move on to part 3 of lecture 4 on radar target cross-section issues in the Introduction to Radar Systems course. Now the question is, how can a target cross-section be determined? First one is by measurement. You can build a full-scale measurement range where you take and you put your object, in this case they look like they're missiles, you have a full-scale missile, and you put it on a pylon. And I'll get into what you make the pylon out of so it doesn't interact with, you're not measuring the pylon. Then you can make scale model measurements. And the second part is we can do predictions. Now what you do typically is you'll take the target. In this case, this is just a photograph of a fighter in F-16, and it's just on top of a pylon. We placed it on top, and the pylon you make out of dielectric foam, very close to the dielectric properties of free space. So effectively, it's structurally sound, but it's on a solid pedestal, but electromagnetically, the electromagnetic wave that hits it won't see it. You can mount it on a metal pylon, and what you do is you shape that pylon to reduce its cross-section and make it very small. You can have just a sharp leading edge and do whatever people need to do to make that very low reflectivity. Or you can make your measurements without the pylon, with just the pylon and no target, and subtract off the background, which is just the pylon, from your measurements, and that indeed would be then the measurement of the target. It's sort of target plus pylon minus pylon cross-section equals target cross-section. That's how full-scale measurements are made. Now this is measurements at a full-scale range facility called RATSCAT of a Johnson generic aircraft model. It's a simple full-scale model that has many of the different features that aircraft have, like a nose, a cylinder, wings, and control surfaces, and this was taken with vertical polarization on transmit, vertical polarization on receive, and targets at an elevation angle of 7 degrees, and the radiation used was X-band 9.67 gigahertz. It's about 3 centimeters approximately. And here we plotted the radar cross-section in dBsm, which is meters squared in dB units. So this is 1 meter squared, 10 meters squared, 100 meters squared, 1,000 meters squared. And we plot it. 0 is nose on. Here is broadside. And here's the tail. Here's the other broadside and the other tail. Plus or minus 180 degree aspect angle as we swing from the tail all the way around 360 degrees to the nose in the center, and then the tail over here. Now let's just start at the nose, okay? We get to the nose, and that's a very, very, very small scatterer. The nose is, the size of the scatterer has to do with the radius, and if you make it a very sharp tip, the radius of the ball that effectively is related to it, so that you get a very small cross-section there. And then as you sweep around, you're going to see a set of surfaces that are going to come into play that we've talked about before, okay? And they're going to be when something is, either we've got an edge that's going to give us some cross-section, like those leading and trailing edge scattering, or it's going to be a broadside effect, okay? So as we move off, the first angle, as we move off 0 degrees, that hits us is this trailing edge of the wing, believe it or not, okay? And right in there is 0, and the first bump we see is the wing trailing edge. And then as we move over in angle, then the leading edge, which is bent back a little bit more than the wing, okay? And so this is the most perpendicular thing as we go from nose on, and we're looking at the whole plane. This is the next most the next most perpendicular, is the wing leading edge. Then we move quite a bit of angle, and you can see here around 70 degrees is when we're 70 degrees off of the nose. The specular of the cone, of the nose cone, comes into play, pretty big. And then when we get 90 degrees, we get a giant specular from the fuselage. That's probably the biggest thing. And then things drop down, not pretty boring, and then we get, on the back of this there was an end cap. So we see an end cap on the back of the missile. So you can see those physical effects taking place. A little later when we do some calculations, we'll put some calculation numbers over this and say, how good were we relative to real measurements? We've just looked at full-scale range measurements. Now let's look at an example of what compact range measurement techniques are like. Here we see a photograph of a U.S. Navy compact range. And below it, this Navy range is at Point Mugu, California. And below it is a schematic of a compact range at the Air Force Research Laboratory at Wright-Patterson Air Force Base. You can see that in both cases, the target, in this case, both are air-breathing vehicles, a fighter, and a little hard to tell on this one exactly what the object is. But they're located on low RCS pylon support systems, and they're inside of what would appear to be a very large box. Surrounding them is absorbing material made of carbon that absorbs any reflections other than the angles you're looking at. The mechanism of generating the electromagnetic plane wave is shown here. We have a parabolic feed, and it sends energy to a subreflector, which is typically at the Air Force compact range is below ground. And then the energy goes up to a subreflector, and the shaping of the main reflector is such that the electromagnetic energy that's sent out is a plane wave. The shaping of the reflector sets it so it's a plane wave going out, hitting the target. Okay? Now, there are a number of reasons you'd want to have these compact ranges. The first of which is you can operate them in any weather inside. And it's under very nice controlled conditions. And you can also use these compact ranges on subscale models. And it's a technique that is used quite often to make RCS measurements, because the full-scale measurements in many cases can be quite costly when they're done on a big, complex range. And you can have multipath effects, which the absorbent material around the compact range mitigate. Okay. Now we have we can do things with scale models and small ranges. Okay. Now here we have a drone, and it's at a 0.29 size, so you don't have the whole plane, you have a model of it. You can make calculations, you can make measurements on scale models, but you have to scale things, and I'm going to go over how you do that. So if you're at full scale and you want to make a measurement at frequency f, and you scale down the size of your model, reduced size, you divide it by, say this S were 2, half size. In this, it's a 30th about, so S is a 30th for this guy right here. And in the subscale, you make those measurements at a frequency S times the frequency you want to know the data for. And then you've got the right frequency. But that's part of the problem. The next thing is, how do you scale the other factors in the target? Well, length scales the same. Length is fine. You scale the time so that the times you look at of the pulse width and things like that, you make them shorter. As I said, you make the frequency longer. the wavelength shorter, and then the permeativity and permeability, which are the dielectric and magnetic properties of the material, are the same. But this thing called conductivity, which is sort of a measure of how good a conductor. If the material isn't a perfectly conducting metal, it's got, say it's a composite, something that's got loss in it or something, then you've got to scale the conductivity of those entities that are on the object. And this is interesting because sometimes what you've got to do is when you do the scaling, it gives you a conductivity for which there isn't anything around, and you have to invent a new material to make it. But anyway, those things can be done. And what you end up with is a cross-section, which is the real cross-section divided by your scale factor to the, your measured cross-section is your real cross-section divided by the scale factor squared. So you'd have to take your scaled cross-section, multiply it by s squared to get your full scale cross-section. Okay? And now I want to go back to that whole issue of scattering, and we went over a little bit before. Remember I said I'm going to tell you once, going to tell you twice, blah, blah, blah. Now that we're in a minute, we're going to go over a couple of examples of how calculations are made. And I can tell you this next 2.5 view graphs, books are written on. We could talk about this for days and days. It's such a complex topic because it is mathematically so, what's the word? It's just an awful lot of mathematics, and it's tough. Even when you get because we're taking Maxwell's equations, which look simple, but when you want to have those Maxwell's equations calculate the cross-section for a very complex target, it gets very complicated to do that calculation accurately with even today's computers. So we're going to go over a couple of the scores of methods that are available to give you a feel for what people do and what are the strengths and weaknesses of the different methods. That's appropriate for this kind of a lecture. Okay? So we have the plane wave coming in, and we've got to satisfy Maxwell's equations. And what happens? Well, the plane wave interacts with this complex object. Let's just for simplicity's sake, it doesn't have conductance in it. It's just a pure conductor. But it's very complicated in shape. And what you do in order to satisfy Maxwell's equations is, it isn't what you do. What nature does is surface currents are induced. And these surface currents vary in time as the electromagnetic and magnetic fields come over the surface in time. And so the currents that are induced change with time. And whenever you have currents changing with time, you generate electromagnetic waves. That's what Maxwell's equations tell us. It's like you either have a current or an accelerating charge that changes with time, and you generate an electromagnetic wave. Well, when you induce currents on the surface of this object, you're going to generate electromagnetic waves, and they are the scattered energy that you see. And we want to measure that scattered energy and see how that compares to the incident energy, the power. And then remember the definition of the radar cross-section. It's 4 pi r squared, and the limit of long distances, the scattered electric field squared over the scattered over the incident electric field squared. Okay? And so in order to get the RCS, the sigma, the cross-section, you've got to know the currents everywhere. And then from those currents, you have to satisfy Maxwell's equations everywhere at the same time. So not just, Maxwell's equations have to be satisfied during the scattering process in order to generate that, solve the problem and get the RCS out. So it's a very complex problem. And we have a lot of different prediction approaches, and I'm just going to go through a few of them. And as you can imagine, they divide up into different methods. And there's a high-frequency approach, and one of them, one of the more sophisticated ones actually that's used is the physical theory of diffraction, where you generate currents, and you add on currents on the object as a whole, and then you look at diffraction and edge currents and add those in, and then you solve Maxwell's equations, solving these integral equations. It's Computationally, it's relatively easy to do. It's good for arbitrary complex geometries. But there's no free lunch ever in this business. It neglects some of the scattering effects. And like diffraction, I'll give you an example. Say, for instance, the wave comes in, it hits this wing, and then bounces off another wing. You know, the interactions it doesn't handle well. And it's applicable only to large, smooth geometries. So it's got, and some of those scatterings, so it's got stuff that has issues with it. Another method you can do will give you the exact answer. It's called the method of moments. You divide the whole surface up into little sub-pieces, and you want each one to be about 1/10 of a wavelength in size, 1/5 or 1/10 of a wavelength in size of your radiation. And if you've got an object that's 30 meters long and a very small 1/30th of a meter is your wavelength, you've got a very large number of objects, okay? So you can do an exact formulation of what the answer should be down to, if you crunch enough, but you've got what you end up doing is change it into a set of equations that have to go in, and you have to invert matrices, and you go wacko with the computational intensity to get the accuracy you want. There are a whole bunch of different codes that are out there. Here are some acronyms for some of them. Yeah, but it's computationally very intensive. And the more precise your model is, the number, these are called facets, the greater the number of facets, and it goes up with powers, I think squares of, you know, since it's an area issue, it'll go up as a square, and that's got some issues with it. Now when we run the physical theory of diffraction predictions up against our RATSCAT measurements, and in red we see here, the physical theory of diffraction. You can see it pretty well is predicting the location of each of the peaks. But the areas between the peaks, here and here, it doesn't do too well. And that's where there's different interactions going on. And this is at a good high enough frequency that this should be good. So it turns out that some techniques work well to get some parts of the cross-section, other techniques work out for others. So now I'd like to, in this last view graph, go with just a simple, what we call a stoplight chart, where we'll say, hey, yeah, it's good, no issue. Yeah, there's some issues. Yeah, there are big issues with this. And we're going to look at, first, if we want to get, for things that are, say, 3 centimeters, aircraft, air vehicles, we want to measure them. We can measure full scale and subscale, and we can predict them with the high frequency methods, like the physical theory of diffraction or method of moments. And how good are they at dealing with calculating the body cross section, the surface details, and taking care of other issues? And what do they cost? You know what I mean? Okay. Well, full scale measurements give you what you want, but they can be very costly. Enough said. You know, there's some significant issues of getting all your data with cost. You'd like to be able to crunch it at a computer and get the answer out. Okay. You'd like to be able, and of course when you make a measurement, you're making it at one angle, one polarization, one frequency, one this. With a computer, if you could do it, you just change the frequency, calculate it. When you do subscale, that'll handle the body shape, the details, and the inlet exhaust. I mentioned we've got this issue with materials. If the aircraft isn't pure metal, it's got composites in it, hey, or stuff with conductivity. You've got issues you've got to deal with. And the antennas and how you deal with the antennas, you have to make a subscale model exactly of the antenna that's inside a radome and stuff. And that can get from red here to yellow. That's an issue that's down in this end of things. In terms of predictive methods, the high frequency methods are very good on body shape, but on surface details and antennas, they're a problem. And there are moderate issues with inlets and materials. Now, relative to prediction with the method of moments, body shape is a real issue because if it's got complicated body shape, you've got huge numbers of facets. But it can take care of surface details very nicely. Inlets and exhausts are a big problem because of the facet issues in modeling them. The materials you can handle quite nicely with this method, and the antennas are a moderate issue. So you can see and cost. There's no green here anywhere, because if there was, you'd go that. But the point is, you get some of the stuff one way, some of the answers one way, and some the other. Okay, now I'd like to summarize. The radar cross-section we see, it varies all across the different targets of interest, and it depends on a lot of different stuff. The target characteristics and the radar parameters. Target characteristics like the shape and material, depends on the radar parameters like frequency and polarization, etc. like that. And there's all that I went over very carefully, the different contributions. The structural composition, like body shape and surface details, they're going to contribute. Propulsion and avionics. Propulsion, that's with the inlets and exhausts, engines, stuff like that. And in the avionics, you're going to have stuff help you fly the plane, like antennas from radars or communication antennas, and seekers in missile heads and stuff. All those kinds of things you've got to take, and they'll give contributions. And the best way to get your estimate of the target signature, i.e. its radar cross-section, is to use multiple tools and roll them up together to get the best signature. Okay. Well, thank you very much for your time. It's the end of this lecture.